Next speaker is Arindam Ghosh, also from ISC.
Well, thanks to Kedar and Shubrata, and happy Shankranti to all of you. Today is supposed to be a harvesting day, so I'm hoping they have got good food for lunch. Okay. But anyway, so I'm Arindam, and I work in the physics department. So what I'm going to talk to you about today is, to some extent, you can call it old wine in a new bottle. It's a very old field. And it's an old field to the extent that the sorry. Yeah, it works. So I was actually I did run out of patience while backtracking the papers when it started getting published. But I think I still haven't got it. But I'm going to talk to you about doped semiconductors in different geometry. And these doped semiconductors were first quantum measurements in these systems started actually way back in 1940s, or maybe earlier. I mean, I don't know. Subir might be knowing that. Because okay. Because, well, but you did work on this in 1980s, which I'm going to highlight as well. So anyway, so it's a very interesting, it's a very interesting system, and it's a system which has led to a large number of concepts in solid state. So it's a kaleidoscope of solid state physics in many ways. Starting from impurity band conduction in way back 1940s, late 40s. You start with metal-insulator transitions and quantum phase transitions in the systems. Anderson localization, scaling theory, you have, variable range hopping, Mott-Hubbard physics. And recently I bumped into Senthil's paper in 2012, which is also saying that there could be some exoticness in the phase that we are talking about, close to the phase transition in doped silicon or phosphorus doped silicon specifically. Okay. So just to give you a sort of major thrust in this field is, this is not the only data, there are plenty of it, but I just wanted to show what people have been involved in right through 1980s and 90s is metal insulator transition. The bulk, three-dimensional systems giving you a true quantum phase transition. And this is a paper from the Carl Schreher group. There are lots of papers from Bell Labs and Thomas Rosenbaum and people, Ravin Bhatt, and there's a whole community that was involved in this research around that time. But look at the interesting bit. What they're looking for is extremely tiny variations of the concentration of phosphorus atoms that can drive a system from a metal to an insulator. And the definition of metal to insulator transition was at temperature equal to 0, the conductivity must go to 0. And this is what the kind of control that they actually possessed at that time, changing the concentration of phosphorus atoms by about a factor, second or third place of decimal per cubic centimeter. So it's this kind of system actually, after that, or throughout the last 60, 70 years, have been subjected to all sorts of experimental, probing. For example, scanning tunneling microscopy, the thermoelectric powers, the thermal measurements, magnetic susceptibility, optical conductivity, reflectance, and we ourselves have been involved in some form of noise measurement. So in this whole process, we did learn a lot about this system. I'm talking about a three-dimensional system still. And just to give you some sort of feeling of numbers, this is a very lightly doped phosphorus doped silicon in which the different atoms, the phosphorus, are sufficiently far apart so that their wave functions do not overlap. And you have hydrogenic donor levels, which is about 45 millielectron volt below the conduction band. And these are very strong on-site interaction and which converts themselves to local moments when they are not overlapping with each other. What was interesting is that when you actually increase the doping concentration, the overlap starts occurring. The impurity band broadens, and there is a metal-insulator transition when the number of carriers increase beyond 3.5 10 power of 18 per cubic centimeter. Interesting part is that now the interaction effects and disorder starts playing with each other, and in spite of the fact that you do not expect a magnetic susceptibility, you do see magnetic susceptibility, and I thought I saw some of Subir's work on this, which we were, around late 80s, early 90s. The typical width of the impurity band when the transition actually occurs is in the order of about 10 milli-electron volt or so, which will become important when I talk to the system that we are working on. Okay, so we learned certain things, and there are a lot of things which remain unanswered even now. So we learned that both disorder and interaction are important at the transition. The effect of on-site Hubbard interaction leads to localized moments which survive in the metallic regime for some reason, and there's a two-phase model that was developed. Then we also have long-range interactions, which leads to Ifra-Shklovsky type of gap in the density of states, particularly close to the metal-insulator transition. And there are other effects like the Altshuler-Aronov correction and so on and so forth. But there are plenty of things which do not understand, even today. At least I do not know whether it has been done recently or not. For example, the puzzle of compensation. So if you are right at half filling, which is essentially no compensating centers, only phosphorus gives you one electron to form the band, then the critical exponent in which the conductivity goes to 0 seems to be half, whereas if you have a little bit of compensation there, which is sort of taking the system away from half filling, you seem to have a completely different critical exponent, and that's something which remains probably mysterious even today. But there are plenty of others. For example, we have the question that if you have metal-insulator transition, what's the order parameter? Do we have a proper order parameter to describe this kind of transition? Do we have, for example, a new phase near the phase transition, particularly what we saw in noise long time ago? We have a very slow kinetics of electrons, asking whether there is a glassy electronic formation. So all these questions continue to remain, and probably will take a long time to answer. But today's talk will actually be taking you away from this particular material framework to a new direction. And what our experimental goal is to take this bulk two-dimensional semiconductors, where phosphorus dopes are distributed all over three-dimensional space, to a system which continues to be a silicon, but there the phosphorus atoms are confined in a two-dimensional plane, and hence the electron transport essentially occurs in 2 dimensions rather than in 3 dimensions. So that's the goal. That's what we would like to do. The reason why we would like to do is there are plenty, apart from the simply doing the fun of it. It's something which, interaction effects are supposed to be enhanced because you're confining electrons in a much closer, in a restricted dimensionality. There's a whole concept, throughout 90s and early 2000s, that whether there would be a metal-insulator transition. So there will be a metal-insulator transition now, although scaling theory of localization actually says that you cannot have a metal-insulator transition in 2 dimensions. Of course, other problems can come up as well, because 2 dimension is sort of a critical dimension. You can have new universalities. There are plenty of logarithmic singularities involved. So there are very interesting possibilities, and which is why we started. And before I tell you what goes on here, let me tell you my collaborators. The hero is Saqib, who is sitting there. He's the one who did all the work, and also sent me some very nice slides. But the original device is created in Australia at the University of New South Wales with Professor Michelle Simmons and her group. I would like to sort of go straight into work, but I think it would be very interesting because this group in New South Wales, they are actually making developing this system for the last 10 years. It's about, first paper came about 6 or 7 years ago, and since then, they are developing this primarily for quantum computation and qubit formation purposes. These are something really interesting work they do. They can position their qubits, their phosphorus atoms in unprecedented precision. using an STM. I'll give you a little bit of a detail how they make the sample so that you can appreciate the complexity involved in this, designing the material itself. So this is something which is a two-atom thick quantum wire, which actually remains a metal down to the lowest of temperatures. So there is another one very recently that they have made a cluster of atoms of phosphorus to which, and in fact, a single atom of phosphorus acts as a quantum dot. And that can be used as a qubit by putting two quantum dots next to each other and changing their couplings dynamically. So that's the interesting bit. I just will give you a quick overview of how they make it. In my view, probably this is the closest to cold atom in solid state in terms of control of how you can create these materials or these devices. So the way they do this is they start with they grow silicon in a high vacuum molecular beam epitaxy chamber, and then they passivate the whole surface with hydrogen. So the hydrogen goes and sits right on silicon, and then they use an STM tip to pluck out the hydrogen atom exactly where they want to. So they open a small gaps here everywhere. And they expose the whole surface to phosphine gas. Phosphine has got phosphorus which goes and binds straight to the silicon, and hydrogen stays up. And then what happens, they heat it up. The hydrogen, so then, after the phosphorus incorporation has occurred, they heat up, the hydrogen goes away, and then this grows silicon again to have these phosphorus atoms sitting precisely at the locations where they want to. Okay, so that's how they could make structures like this, in which you actually have almost a two-dimensional solid of phosphorus atoms at completely tunable length scales. When I saw this, maybe 5 to 6 years ago now, felt that this is a beautiful technology to make extremely small structures, but this has the potential of doing something which is nothing to do with maybe quantum nanostructures, but something completely different, which is in two-dimensional physics. And from there, we started collaborating. Now it's formal collaboration with them for the last 5 years or so. So silicon and germanium, you grow that, and you have the surface exposed, and then you expose that. You do not use any STM tip, but you just expose the entire surface to phosphine. What happens, phosphine comes and sits randomly at various places on silicon. Then you heat it up, it's a desorption of hydrogen, and then you grow the whole silicon again to encapsulate the whole structure to make a two-dimensional electron gas inside the silicon matrix. So that was the experimental achievement that has been going on for the last few years. So what we have here is, this is the crux of the summary of the whole thing. We have a two-dimensional impurity band inside silicon. Yeah. Yeah, absolutely. And this has been checked. Yeah, it is also feasible. It probably is a little expensive on time to make phosphorus exactly positioned in perfect array, but in principle it is possible. And they have made tiny arrays, because you see, you have to take out each and every phosphorus atom using an STM tip. So making the entire structure takes time. But it is now completely feasible. Yeah. And yeah, so that's why I was saying the control-wise, it's almost approaching the cold atoms from the solid state perspective. So what we have here is a derivative of the classic system of phosphorus doped silicon, which are entirely compressed to one in 2 dimensions. It's of course much simpler in many aspects. So doing a theory as well as experiment is much easier. These samples, for example, Saqib has measured, absolutely remain unchanged over the years. So extremely clean and very, very robust and strong samples. And simpler because we don't have unknown lattice distortion like DX centers, the kind of problems which people expect for other doped semiconductor systems. Yeah.
So if there is any lattice distortion or strain,
Yep.
can it bring some silicon states to the formula as well? How much is the gap?
Okay, so that is only when you have a lattice distortion stress. One of the huge advantage of phosphorus doped silicon is, you see phosphorus and silicon are right next to each other in the periodic table. So it's a perfect Yeah, just you replace silicon and put phosphorus, no one could see anything anyway. So that's one of the huge advantages of working with this particular system. It's very, very well defined. And people know about it, and there's no strain. There has been work which apply external stress and look at metal insulator transition, but that's different. Okay, so, and there is it's in a cross diffusion of phosphorus across the planes is very, very little, which is why it's a true two-dimensional system, which is probably 1 nanometer or less thick. Okay, and we can tune the interactions, you can tune its transport properties by changing the doping concentration or also using gate, but we haven't done that part very carefully. So what we do once we have a system like this, we make a simple device, and the device looks something like this. We have silicon atoms with interdispersed phosphorus everywhere, leading to a two-dimensional system. As far as we are concerned, the silicon is essentially a vacuum. It's not just silicon. We have used silicon or germanium, for which all it does is provides two different dielectric environments. Phosphorus is essentially the crucial component in the whole process. Okay, so I'm going to talk about this very quick. This is the flow. I'm going to show you the first quantum transport measurements in these two-dimensional, weird or very new kind of two-dimensional electron gases. I'm going to show you that when you push this system towards low doping concentrations, which means the interaction becomes very strong, U by T becomes strong, then you actually see pretty convincing evidence, according to us, of spontaneous time reversal symmetry breaking. Now, that would have been the end of the talk, but then we have been doing something else to understand whether the interacting regime is interesting and really non-trivial. And we have done some other measurements. I'll just give you some glimpse of that experiment, of what's going on right now. So, give you a phase that we have covered so far. So if this is a two-dimensional electron gas, this is a planar view. You can see the distance between two phosphorus atoms is Rp, and this is the Bohr radius. The doping range that we have covered is approximately 10 to the power of 13 and 10 to the power in that order of magnitude. Now, I would like to make a quick observation here. Typically, the system is constrained within about a 1 nanometer region thickness, which means that effective three-dimensional doping density will be in the order of 10 power of 20 per cubic centimeter, which is very, very metallic system. However, we see a very strong tendency towards the transition actually even at this density. So probably the interaction effects are already very strong in this doping density region. So these are the germanium and silicon devices that we have measured. You can see from these doping densities, we can calculate the overlap integral, and typical overlap integral in our systems is in the order of 10 to 50 milli-electron volt. Again, it is reasonably sort of believable, because that's the number even for three-dimensional system, we get the same stuff. And if I take the on-site interaction, U is in the order of 50 milli-electron volt for germanium and 200 milli-electron volt for silicon, which means that from within the density range that we have covered, we actually have very high density region, which is the least interacting. The U by gamma is in the order of 1, whereas extremely high density, high interactions, a low density region here, the U by gamma can go to up to 10. So that's the range that we cover, and I'll show you that the nature of transport becomes drastically different as you go from U by gamma of 1 to U by gamma of 10. This is the Drude conductivity, and this is the high density region where, and this is by the time it comes here, it starts showing interesting signatures. I'll tell you what happens. So there are two batches of devices. I put them together. The black ones were created when they were optimizing their setup. The other ones, the colored ones, are the one which we have done on a much better system, much lower defect configuration, much higher mobility. But even then, what was particularly interesting is that when we started measuring or pushing ourselves to even lower value of density, we could never do that. We could never find a working sample beyond this particular density. and this was really surprising, because there's no reason why you really cannot make a working sample by reducing the doping concentration by less than 10%. There should be a fairly easy thing to do, but we could never actually get a working sample here. Even this particular sample, if you measure it from different parts, it actually shows very different results, which was absolutely not the case for any of the device at higher carrier concentration. So I actually split it in two parts. I have got a measurable part, and this is where the devices are very well behaved. And here, this particular region where we didn't find any working sample so far. Okay. So I do not know whether we should talk about it as a critical phase boundary or something. I do not know, but that's the experimental fact that remains for the time being. If I quickly take a look at it, the conductivity of this density is roughly around 4 e squared by h. All samples, except this one, I'm not going to talk about this one too much. I'm going to confine myself here where the device characteristics have been particularly repeatable and we have sufficient reproducibility. Everywhere, at low temperatures, we see conductivity going down logarithmically with temperature, which again shows a metallic kind behavior. So it's a quantum correction to conductivity. Both weak localization and electron-electron interaction will give you the same kind of a behavior. You can see this one is high density shows smaller correction. The lower density ones here show much stronger correction, but all logarithmic. Now we start first getting into the quantum interference process and started measuring the conductivity as a function of the magnetic field, perpendicular magnetic field. You see, we've covered approximately 4 orders of magnitude of magnetic field. In this regime, it is B square, which shows that it has a time reversal symmetry of some at least nominally. I have taken this particular sample for your, as a reference. You see, at very large fields, it starts dropping, but that's very easy to understand. This is essentially correction from the magnetic field dependence through the conductivity itself. It's a completely classical correction. There is no ambiguity there. We can actually calculate without even a fitting parameter what's the correction will be, and we can immediately subtract it from the observed conductivity versus magnetic field. So if I do that, and also assume that because it is a perfectly diffusive system, the interaction and correction to conductivity is perturbative and almost zero as a function of magnetic field, we can actually, after subtracting this part, we'll get only the quantum interference component in the quantum transport. So when I do that, I get this, which is very nice at very high magnetic field. The entire quantum correction is gone. Conductivity has increased from here to here, and amount of increase is determined by the phase breaking length of the system. So these solid lines are free electron Hikami fit, which tells you that this is a system where weak localization is probably valid. I'm not entirely sure, but probably this is this one, yeah. So this is this number. The maximum change is the free electron single particle universal correction to conductivity because the quantum transport at low temperature, and given by log of tau phi by tau naught. You can actually get tau phi or the phase breaking length from the fitting as well. Yeah. Yeah, I'll show you. That's there. That's there. There are a couple of slides on that. Okay. The problem is, and this is where we started, is when we start increasing the interaction in the system and look at the net quantum correction to quantum interference correction, we find something really unexpected. So something starts happening here. In this particular sample, which is very low interaction, high density sample, if I look at the total correction to conductivity, it actually approaches the free electron value. And this almost 1 is where the free electron value expected, and it reaches there at very high magnetic fields. So it's almost behaving like a standard free electron system. Then you increase the interaction by reducing the doping, and then you see it's now no longer, there is no, by the way, this is pure and simple data. There is no fitting involved here. Only thing we have done is that we have taken the tau phi value from the magnetoresistance curve and normalize the whole curve by what is expected for a free electron model for that tau phi. And you see that it's actually is not reaching the value of 1, which is expected for free electrons. If I increase the interaction even more, the quantum interference is suppressed even more. So actually, as a function of doping density, the quantum interference correction starts going lower and lower. So we then started measuring all samples and put them together, and this is how it looks as a function of the corresponding Drude conductivity. So as you see, the Drude conductivity is less as you reduce the doping density, and in this axis you plot the quantum interference correction alone, and you see for all samples, irrespective of when they were made, what was the dielectric, germanium, silicon, they fall on the same line, which seem to suggest that the quantum interference correction is going to collapse at a finite value of the Drude conductivity. So this region is the strange region. And this is the part which can lead to questions, for example, whether is this some form of a real quantum phase transition, or is it something completely different? We don't know the answer of. Is this the minimum metallic conductivity that we always eluded from in the three-dimensional cases? Or that's nothing else. I mean, it could be completely true. So from experimental point of view, we wanted to actually not go into those questions at all at this point of time, but we wanted to say, okay, why is the quantum interference correction getting suppressed at zero? That's as a function of density. So is that because, for some reason, the time reversal symmetry of the system is getting suppressed? So we wanted to have a direct probe to that, and that direct probe is universal conductance fluctuations. I'm going to give you a very brief introduction to why universal conductance fluctuations is actually a far better probe, or a far more fundamental probe to time reversal symmetry than quantum correction to conductivity, because quantum correction to conductivity is, you can have electron-electron interaction, which is coming in an unknown manner, maybe, and there can be certain questions raised. But UCF can actually give you a very strong evidence, or very convincing evidence, whether the time reversal symmetry is there or not. So, how? If you have standard magnetic field dependence, you will know that UCF essentially manifests itself in aperiodic fluctuations of order of E squared by h in conductance, and that's essentially because as you change the magnetic field, you are changing the interference pattern, and these kind of systems are extremely susceptible to the interference pattern, and which is why it gives rise to changes in conductance in the order of E squared by h. Okay? You can get the same change by changing Fermi energy, or by changing the disorder ensemble. And that's what's very interesting, because if you change the disorder ensemble, then using ergodic hypothesis, that reflects into a time-dependent noise in the system. For example, like this, random fluctuation in electrical conductance. And if I take a power spectrum, you get a 1 by f noise. So this advantage of this is that you can now look at the universal conductance fluctuations very closely in magnetic field. We don't have to vary the magnetic field and see the universal conductance fluctuations. But we fix the magnetic field and look at time-dependent noise, which essentially reflects the ensemble of the fluctuations. So you can actually see the UCF magnitude at every magnetic field. And that was crucial in this experiment. Okay. So what we did that. I'll just quickly take a minute to sort of go to a different direction for a slide or two. We have been working on this system because this is very interesting, in which silicon is having two-dimensional electron gas below the surface, which is different from standard silicon MOSFETs that you have in your computers. From experimentalists' point of view, it's actually a very interesting system, because this particular kind of devices show the lowest noise magnitude in comparison to any system that you have in the market today. It's actually orders of magnitude lower. So this is what Saqib's first experiment was. And we looked at the pure noise magnitude-wise, it's way, way below the standard silicon-based devices you have in computers and other electronic systems. And the reason behind it is that the dangling bonds on the surface are actually made immobile because of mutual interactions. And recently, Saqib completed this new interesting experiments on quantum wires, which show very, very high conductivity even at low temperatures, and found that these quantum wires probably are quietest quantum wires, even in comparison to carbon nanotube and other kind of single crystal materials that you encounter very frequently. I'll not go into that direction, but let's move back to what I was trying to say. I wanted to show you that why universal conductance fluctuations is so sensitive and so fundamental probe to time reversal symmetry. I'll give you two approaches. Both are identical in its final conclusion. You see from standard UCF definition is if you have a system in which there are multiple propagating channels, then UCF is essentially a cross correlation of between two interfering quantum propagators, which means that it will have contributions from the diffusons. That means in which you have an area and this is covered in same sense paths, or couperons where the same area is covered in opposite senses. So for each diffusion, you can actually create exactly one couperon, which means the total contribution is exactly twice of either diffusion or couperons. So which means that if I apply a magnetic field which is higher than the phase breaking length, then I'm going to destroy the couperon contribution, which means that the noise will come down exactly by a factor of 2. Exactly by a factor of 2. And that's something which is very important. I would say, that part is not there in weak localization correction to conductivity. You cannot say exactly by how much it will come down by. But noise comes down exactly by a factor of 2 if you remove the time reversal symmetry from the system. And that's the part which we have used in these experiments. Yeah. Sorry, second? Yes, it is true also for interaction corrections, absolutely. It depends essentially from the symmetry of the Hamiltonian. You see, this is a random matrix approach. So you have, again, the Wigner-Dyson ensemble in which the interaction, UCF, is inversely proportional to the parameter beta. And when you have a B less than B phi, you have a real orthogonal time reversal invariant Hamiltonian. And when you are in the time reversal symmetry is broken, you have by magnetic field, for example, the beta goes to 2, which means that the noise comes down again exactly by a factor of 2. So both approaches are consistent with each other and leads to half of change in UCF magnitude by half. Now, this also tells you another aside. Again, if I destroy the spin degeneracy by applying a very large magnetic field so that the field is above the Zeeman field, then there would be a change in the level degeneracy as well as the number of independent sequences. And that leads to, effectively, another factor of 2 reduction in noise when the field scale is very large and spin degeneracy is removed. We'll see that later. So we measured the UCF 1 by F noise at various, in all these samples, devices as a function of their doping density. And we look at the temperature dependence. This 1 over T type of temperature dependence is hallmark of UCF because as you go to lower temperature, your phase coherence length increases and the averaging goes down, which is why the noise increases. So this is, again, a clear signature. UCF is the major source of noise in your systems. Yeah. Yes, samples are way, way bigger than the phase coherence length. Phase coherence length is in the order of few hundreds of nanometer, whereas I think Saqib will be able to say better, and these are hundreds of micrometers in size, the samples. So at least 3 orders of magnitude. Oh, we do. Particularly when you go down to smaller sizes, we do. Magnetofingerprinting actually becomes better in smaller samples because you need to have, yes, with smaller samples, we do. Actually, this particular sample, which was measured in one of those silicon devices, so this is measured. This will be in the order of 10 here, it's given. These are sample sizes. Phase coherence lengths remain the same. It's the same size of same sample of different sizes. So phase coherence length is about 100 nanometer, I think. Is that right? 450 nanometer for this one. This is the length of the sample. From 1 micron, where you see maximum magnetofingerprinting, and this is 30 micrometer, which is least amount of magnetofingerprinting. This is 0.2 Kelvin, kT by h cross d by kT. I have to check exact number I don't have offhand. Do you remember a second? What's it? Yeah, so it's thermal length is actually longer at this temperature than the L phi. So the dephasing is actually dominated by the interference rather than thermal fluctuations. Yeah. 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 That's correct. That's right. Yes. That reflects the magnitude of UCF that you have. Okay. So for 1/f noise per se, you don't need to worry too much about. It's the magnitude of it is a contribution from quantum interference. So so this is, now I'm going to show you what happens in a low density cell system. As we expected, there would be a factor of 2 reduction at the phase breaking field, and that's exactly what we see. You can see there are 2 factor of 2 reductions. One happens at the scale of B phi, where the phase breaking length is, or rather, gives you the one flux quantum in an area of L phi square, where the phase breaking length area. And then another one comes right here, which is the reduction or the absence of spin degeneracy, BZ. When the Zeeman field comes in, the spin degeneracy goes away, and an additional factor of 2 reduction happens here. So this means that this is perfect. This is exactly what a free electron system will behave, and we have got that. Now we start looking at okay, so this part is Cooper-Round plus diffusion, and this is just the diffusion. And then this one is next one, which is the interacting system. And the surprising bit here is that we found that the first increase or reduction at the scale of B phi was completely absent. So this is, again, clearly UCF dominated, because we are definitely seeing the second factor of 2 reduction at the Zeeman field, which means that the system is behaving as if it's a free electron system at high magnetic fields. But for some reason, at the low magnetic fields, there is no factor of 2 reduction. So when we saw that, we started measuring all of them systematically. And I'm going to show you what happens. This is no factor of 2 reduction at these fields. This is all the data put together, in which we looked at only around the 0 magnetic field region, which is where what happens at 0 magnetic field. For this particular sample, we have perfectly factor of 2 reduction, which means time universal symmetry is perfectly intact. Then we start increasing the electron interaction, or start decreasing the density, and you can see the next one comes here. These 2 are somewhere here, and by the time it reaches the final ones here, there's absolutely no change whatsoever around the 0 magnetic field. So question that we automatically ask here, yeah. The metal insulator transition, we never see an insulating phase per se. So in sense, all of them are in the metallic regime, but this is the closest to the metallic regime. That's right. That's right. So so this is about 5 10 to the power of 13 per square centimeter. If I reduce to 4 or 3, then it sort of jumps. So this is metal, but it's very close to the metal insulator transition. So this is what we did after that. We took this ratio and plotted as a function of the effective dopant separation, and we see that at very low dopant separation, which means strong overlap, this is perfectly fine. But at sufficiently large dopant separation, there is there is no clear time universal symmetry. The noise has come down exactly by a factor of 2, even at 0 magnetic field. So what could be the origin? So we started looking for different reasons. One of the possibilities is there is a magnetic ordering, because there are a lot of magnetic moments, maybe. So we looked at Hall conductance, and we found that whether it's here, this one, and this one, we found there is no anomaly in the Hall conductance. And if there's a permanent magnetism, then you should see anomalous Hall effect. But we do not see any anomalous Hall effect, which means there is no obvious magnetic ordering, or at least experimentally perceptible magnetic ordering there. Any magnetic. Anything would give you an anomalous Hall effect if you have a permanent magnetism there, but we don't find that. So there is no, we don't, in none of these samples show anomalous Hall effect at any temperature. Parallel magnetic field. So this is something which you wanted to know, and we will show you that this actually, in some sense, agrees with what happened way back in 1980s about in three-dimensional SIP. So we apply a magnetic field in the plane of the two-dimensional gas, and we found that when it is at high density, this is a low interaction, there is no feature at zero, around zero value. But when it's at low density, interacting samples, then you see at right close to zero, there's a decrease in the conductivity as a function of magnetic field, but then it sort of starts going up again. Now this part, this going up, is something which is a trivial effect. It is because the system is finite size. It's, after all, 1 nanometer or 1.5 nanometer thickness. So there is a, that finite size effect leads to the positive logarithmic magnetoconductance in parallel magnetic field. What's interesting and different between high and low density is this part where we see a negative region, negative magnetoconductivity in parallel field. Now that can also be understood because people have discussed this in other contexts, and this could be if you have got magnetic moments in the system, isolated magnetic moments which are doing spin flip scattering, and then when I apply a parallel magnetic field, we are freezing these isolated magnetic moments, and hence the spin flip scattering is gone, which is why the system increases its quantum conductivity or quantum correction to conductivity, because the L phi has gone up. So that's something which could explain. And if I take from our analysis, which I'll not go into the detail, we actually did do some estimation of how many local magnetic moments could still be there in these systems. It comes to about 2 to 6%. That means 2 to 6% of the phosphorus atoms are probably behaving as local moments in the plane. Well, I mean, it could be locally, but there is certainly no magnetic ordering that can come from these 2 to 6%. I mean, there's no long-range magnetic order, but there could be local condo. Oh, this minimum? Well, I don't think so, because, okay, first of all, I didn't include a data where we actually looked into this. This is a very linear variation. It's not really a logarithmic. So I don't think it's condo, but I can show you the data more clearly in a discussion later. But we actually found that this is a believable number because we have, by simply looking at it as a parallel scattering mechanism from spin flip scattering mechanism from isolated magnetic impurities. Okay, so we are more or less here right now. I mean, I do not know the answer to the question why the system is showing a spontaneous time reversal symmetry breaking. And it could be many possibilities, and I do not want to get into that. We have heard this particular possibilities over the last few days over here. What experiments we are doing these days are, or we have it in pipeline, are thermal transport to see really whether the system actually is thermal conductor, a better thermal conductor. Problem is this is a two-dimensional system, which is makes it very difficult, and they have a substrate. So thermal transport becomes very difficult to do. So we are trying to sort of think about some clever geometry in which we can do thermal transport. But before I finish, I would like to give you a few slides. How much time do I have? Can I leave 5 minutes for question later? Okay. Okay. I'll just show you. I'll show you some experimental results that we haven't published yet, and this is on whether this phase that we are talking about in 2 dimension is actually unique, or this is something which, before we go into this thermal measurements and other directed probes. So what we did is we were having fun, and we wanted to just put some superconducting leads instead of metallic leads. And the reason why we did it was to see, if there is some form of a magnetic ordering, then ferromagnet superconductor interactions can lead to something interesting. We do not know what's going to happen. But it did turn out that when I have superconducting leads, this system behaves very, very differently than when the system is non-interacting. So, this is a standard Hall bar that we measure, okay, in which we have very large distances. So assume that these are aluminum leads, and which are aluminum leads. The two-dimensional electron gas is this, with the dimensions of the two-dimensional electron gas is much, much larger than the superconducting coherence lengths in the system. So superconducting coherence length is about a micron at the most. Probably for lower densities of it will be even shorter. So this is way larger than the superconducting coherence length. And we all measure the 4-probe resistances mostly. We do 2-probe as well, but the data I'm going to show you are all 4-probe. That means, for example, I pass a current between this contact to this contact and measure the resistance between this and this contact. So technically, whatever happens near the contact should be completely material to you. Okay. So if I apply now a parallel magnetic field, and this is something which is, a recent, well, it's not recent data, but we see something really strange. So this is now a 4-probe resistance of this sample as a function of parallel magnetic field when the conduct is superconducting. Below 20 millikelvin it is superconducting, above a millitesla, above 20 millitesla, which is the critical magnetic field, critical electric magnetic field of aluminium's contacts. The system becomes perfectly normal here, but around the superconducting region, it starts behaving weirdly. So there is apparently a strangeness in this part, but we will leave it aside for the time being. What I'll show you what happens when I apply a magnetic field perpendicular. And when I apply a magnetic field perpendicularly, you will see there's a very sharp peak right at magnetic field equal to 0. Okay. Now this is something which is very interesting because this has been seen before in other systems in different contexts. This normally is taken as a signature of a supercurrent. Why is that? I'll just quickly show you on the board. So you see a supercurrent in current versus voltage looks something like this. Our resistance measurements is essentially a differential resistance measurements where we measure the derivative of voltage dV di. So that means when the system is, when there's a supercurrent in the system, then you are measuring really some form of a diverging component dV di, and that other way around something, somewhere here. This is like this. This is a diverging component of dV di, which can, and people have seen this in other systems where you get a sharp peak at dB equal to 0, and that moves. So the question is why there is a supercurrent in the system? If we agree to accept it as a supercurrent, it is completely surprising that this system, which is hundreds of micrometers in size, no, wait. It's here. Supercurrent is like this. This part is far too close to 0 for us to understand, for us to, this part. Okay, but let me put it this way. Yes. No, that's what. But resistivity, it's a resistance measurement, which are differential resistance measurements. What I'm trying to say is that anomaly here is an effect of superconductivity, because when we started doing this as a function of temperature, that disappeared exactly when the system becomes normal, the leads become normal.
Has anyone done this kind of study before for other superconductors?
Yes, topological insulators, for example, recently. And there have been other systems which show exactly the same peak, and which is why they take that as an evidence of a supercurrent. But there you see in most of the other studies, the system size we were talking about is just about 1 micron to 2 micron, where it is believable to have supercurrent. The problem in this is that we are getting identical experimental feature, but the system is approximately 3 orders of magnitude larger, or at least 2 orders of magnitude larger than what a supercurrent would give. So we don't understand this at all. But it is connected to superconductivity. There's no doubt about it. You can see the suppression of of this peak the moment aluminium becomes normal. Okay. Second thing, which is another interesting bit, is non-locality. So what we do here is that, again, the same, take the Hall bar, and you pass a current either in this direction, or you pass a current in this direction, and measure the voltage here. Now, given the size of the samples, which is about 100 micrometer here and 20 micrometer here, the classical non-local resistance that you would measure is in the order of 1 milliohm. That's these are well-defined or well-known expressions. What we do is when aluminium is superconducting, we see about 5 orders of magnitude increase in the non-local resistance. And again, the non-locality is completely destroyed when the aluminum becomes normal, either by a magnetic field or by temperature. Okay. We are again talking about a system in which we pass, in this particular case, we pass the current in this particular sample. This is the highest interaction sample. We pass the current here and measure the voltage here. We expect typically about 1 milliohm. We are getting in the order of 500 to 600 ohms. Yes, next slide. Next slide. So this is as a function of temperature. So last slide is this. So this is two systems. One is here, which is the system here, strongly interacting, where you see this huge non-local resistance of 80 ohms or so. The moment the time reversal symmetry is returning, that is low density, high density samples, this is the non-locality. Again, with aluminum contacts, identical device geometry, there's no difference in terms of from device to context. So we would like to sort of believe that this is because of the system, the non-locality of the interaction and superconductivity leads to some very weird behavior in this kind of systems. So I would like to leave you with this. Of course, I'll be open to any questions and discussions. I would like to quickly summarize. It's probably the first time that detailed quantum transport in this new class of two-dimensional systems close to metal-insulator transition. From device aspects, from experimental aspects, it's probably unique because it shows the lowest noise that available or in silicon-based nano devices. It's a collapse of quantum interference correction when you take the system to near metal-insulator transition. Universal conductance fluctuation shows, I thought, pretty convincing evidence of time reversal symmetry breaking spontaneously. And new surprises with superconducting leads, which we have absolutely no clue about. We actually don't have a clue about why even the time reversal symmetry is breaking. Thank you for your attention.
Thank you, Arindam.
Right. Sorry.
I'll just come to you. Okay. So one thing I want to understand first is the difference between time reversal symmetry breaking and spin rotational symmetry breaking. So in condensed matter, the way as far as I know, time reversal symmetry breaking is when you have a magnetization, so you can check it by anomalous or Hall
we don't
effect.
have. That's what.
Yeah.
That's what
No, I'm coming. Let me complete.
Yeah.
Or night shift and all. But spin rotational symmetry breaking can happen spin orbit coupling, and so if you have a spin rotational symmetry breaking, I guess you can still see this quantum interference, I suppose. So now let me see why we can get a enhanced spin orbit coupling in your system, because silicon, germanium, spin orbit coupling locally.
So that we did think about it. There is no direct way. Silicon, phosphorus.
No, because because when phosphorus goes there, locally breaks the inversion symmetry. So it can give rise to enhanced. No, let me complete.
Okay.
It can enhance some Rausbach spin orbit coupling,
okay.
And people have studied inhomogeneous Rausbach spin orbit coupling, and they have some powerful predictions.
Well,
so
at least in bulk phosphorus doped silicon, I don't know of any report of spin orbit coupled, because that normally reflects. If you have local spin orbit coupling, it will will reflect in many experimental probes. Quantum transport is one, looking at anti-localization if you have any. I do not know of any evidence.
If you have inhomogeneous, the predictions are very different from a homogeneous Rausbach spin orbit coupling. Inhomogeneous means locally, no?
Yeah, I agree. That is a possibility that this is not a homogeneous system. This is a very disordered system, randomly placed.
Yeah.
You do see there are very weak spin orbit effects in phosphorus silicon, just seen in NMR, but at very low temperatures. But I don't think that affects anything.
Yeah.
In what?
In silicon, which is the single layer silicon. The reason is because the Rausbach spin orbit coupling can enhance.
Okay. All right.
Wow.
I mean, your phosphorus is embedded inside silicon. It's not on the top surface.
No, it's not.
Yeah. I mean, so assuming spin orbit coupling is 0, then one can ask, is the time reversal symmetry breaking in the spin sector or in the orbital sector?
Correct.
So given the fact that you see the factor of 2, the second factor of 2 at large
Correct.
b,
It looks like
suggests
orbital
that it
sector.
probably should be in the orbital sector.
That's, I was coming to that, exactly. We have
Okay.
to already have the question answered, because we see the second factor of 2,
Yeah.
which has to means that spin degeneration is broken there.
So then I'm
So-
still a bit confused about the anomalous Hall effect. Wouldn't there be some anomalous Hall effects there? Or
We don't find any.
Yeah.
There is no
I
anomalous
don't know
Hall
if
effect at all.
anybody has any ideas.
Yeah, so I'm also puzzled that the only signature of time reversal symmetry breaking is from the universal conductance fluctuations.
And suppression of quantum interference.
Yeah.
Both.
But the question is, I mean, both of these results are, as far as I understand, are a result of weak coupling perturbation theory.
Okay.
And if you're close to metal insulator transition, you might be also close to some kind of Mott transition. And
Correct,
it's
absolutely.
not clear that any of this theory still holds. So I wonder if maybe that is what bringing all of these corrections down, because you're
Well,
and
if
then
that's
there doesn't have to
could
be
be, but-
any broken.
Well, you're absolutely right. I mean, point is, well, that probably would mean that we are close to Mott transition.
Yeah.
I mean, the lowest conductivity we could measure is about 4 or 5 e square by h. Below that, nothing works. So if there is, that means that that's the Mott minimum metallic conductivity that we are seeing in this system. That could be one of the situations.
Well, I mean, but in any disorder metal, there is, for arbitrary interaction strength, a theory of UCF, which is why I asked about, I mean, for interacting electron, they have some parameters, F or something.
Yeah, but that comes
Is
in
it
the
still a factor
conductivity.
of, huh?
That
Yeah,
comes in
but
conductivity.
for the UCF, you still get the factor of 2 for all,
Yeah,
for all the Fermi liquid
that's
interaction
precisely the
parameters.
case. Yes,
okay.
yes. So that's why UCF was such a powerful probe. Conductivity gives you an understanding, some directions, but it actually cannot tell you for sure that there is a suppression because of quantum interference alone, because that parameter F, which is Fermi liquid parameter, actually, which increases. And the entire, the quantum, this metal insulator transition community, when they were looking for two-dimensional metal insulator transition, they went on fighting on that particular parameter, that in some sense F is larger as you go to more interacting systems. So there's a whole lot of uncertainty in quantum correction to conductivity, but UCF is immune to that. I do not know whether that will be very different right at the transition or in the insulating side, but given the metallicity, because in all of them we see log T dependence of conductivity.
When this diverging correlation length is above this phase breaking length,
Right.
then I think all of this theory should break down. It's not right? Then you have some, okay. Yeah.
I don't know. I mean, a diverging correlation length requires, again, proximity to Mott insulator transition. Yeah.
Any?
So I'm not an expert in this field, but so maybe something very stupid. But the random matrix theory results are essentially for a non-interacting disordered system, right?
I mean, I think you have to ask the theorist here. So
Is for non-interacting disordered system, and here you have large interactions. And as you come close to the metal insulator transition, there is this wave
Yeah,
function multifractality that would come into play. So you need to take that into self-consistency,
agreed.
right?
But you see, sorry, before, can I answer the question quickly once? You see, we are seeing the deviation from that situation only in the low magnetic fields. Even in our most interacting samples per se, we are seeing the second feature, which belongs to a non-interacting theory per se. I cannot say what happens when you incorporate interaction, but the fact that we are able to connect to the second factor of 2 reduction means that the original theory of UCF as a function of magnetic field is valid, even though the interaction in our system is actually pretty strong. Yeah, Alexei. No, that's exactly what I said. We could not measure any sample which is below the doping density of 3 × 10⁻14 per square centimeter. The samples, none of the samples worked. So,
but is it that
okay.
you just cannot
I
do
have,
electrical measurements?
well, I have some data. I'll show you sometime when we discuss maybe. Sorry? They don't work in the sense that they show completely erratic behavior from, you know, and different parts. We can make contacts. We actually have some data. I can show you, but you know, this talk would have gone 1 more hour then. I can show you at some other point of time, or maybe in discussions whenever you want to. But yeah, we do have some data on that. I have the slides. First of all, the close to zero magnetic field, the behavior is completely different. Okay, right there. Okay, it actually shows a very strong dips, and in some length scales, in some other length scale, it shows a peak. You know, very, very erratic and irreproducible. Even from the same wafer, if you go to different regimes, it shows a very different behavior. So the problem here is we are at a fix of how we interpret it ourselves. But you know, I can simply throw the data in front of you. You do whatever you want.
Okay. So
That's precisely the case. Yeah, that's right. I mean, I think the problem will come at different levels. I think the problem will come because of contacting, because it's an insulator, making a metallic contact to that. How we do that is a completely unknown question. Second is there would be huge contact resistance, but that we can still take into account by proper experimental geometry. But overall, I think what we found is that, say, for example, Hall effect. We saw Hall effect pretty well defined even in the strongly interacting SAM system here. But there, the Hall effect essentially shows a peak at b equal to 0, and there is no clear, you know, 1 over n kind of dependence in Hall effect. So neither Hall effect nor, in spite of the fact that, you know, our experimental geometry is extremely well defined, the samples are extremely stable, but all these parameters essentially start looking completely different in that system. But I have to show you to, you know, give you a feeling of it.
Last question.
Yeah.
Are there some other measurements you can do that would directly probe whether there are some local moments forming if you're really near a
local moment formation probably is true already, because
even at
parallel magnetic field dependence, and secondly, the fitting of the Hikami formula actually gives us that there is a formation of local moments in our strongly interacting samples.
in the strongest interaction.
In the strongest interaction, and that is not there in the low interactions. In the strongest interacting samples, there's about 2 to 6% of the phosphorus atoms have been converted to local moments, but they do not form a sufficiently, you know, magnetically ordered phase in that. Yeah. That's right, correct. But we have also done experiments on various geometries, and we do not really see any anomaly in that sense. Oh, Rajdeep.
Is there a question? Oh.
Yes. Okay. I actually can show you the problem with Onsager reciprocity. You can see the last graph that I actually showed. There are 2 traces, okay, in which we measured we sent the current from here to here and measured the voltage between this point and this point. You can see the red one. But when I send the current from here to here and measure the voltage between this point and this point, we see the black one. So the Onsager reciprocity probably is sort of there or not there. It's up to you to decide. But I'll leave it at that, actually.
Okay, let's thank Arindam once more and break for coffee. So we meet here again in 25 minutes for Mukul's talk.